Junior Certificate 2019, Technical Graphics Higher Level, Section A, Short Questions. Throughout this video, I have used coloured pens to highlight construction lines. You should use pencil and light lines on your own drawings.
Okay, so we want to take a look at the 2019 short questions, Technical Graphics Higher Level. And the first short question here in section A, it says fill in the label for each diagram by selecting from the given list. So over here we have a list of different terminology associated with circles, and we have to fill them in here. So here we see a circle with a line touching the circle, and the line is touching the circle at a point, at a single point. So therefore the first one, it's a tangent. A line that touches a circle at a single point is referred to as a tangent. Moving over to this one here, we have a circle with a line going through it. And this time we've dealt with tangent, so we have quadrant, sector and chord. Now, a chord is a line that goes from the circumference to the circumference but does not go through the center. So therefore 2 is a chord. Third one, we have this area of the circle that is enclosed by a radius on this side and a radius on this side. So an area of a circle that's enclosed by 2 radii is what we refer to as a sector. And then we have a quarter of a circle here, so we have a quadrant. Now, when you're filling in the answers in here, put in your answers in block capital letters. Again, keep your work nice and neat at all times. So nice and neatly, we fill in the answers: tangent, chord, sector, quadrant. Moving on now to question 2. We are shown a perspective drawing. So, reading the question. The figure shows the incomplete perspective drawing of an electric piano. A 3D graphic is also shown. Complete the perspective drawing. The first thing we must do when we're dealing with a perspective drawing is that all lines must converge onto the vanishing points. So any line that is moving in this direction here is going to converge on VP1, and all lines moving in this direction are going to converge on VP2. So I've extended that line to VP2, that line is also brought towards VP2. In relation to this line here, you have to first of all draw a small vertical line and then bring that back over to VP2. And then all of these other lines here go and converge on VP1. Now, what I should have mentioned in the first part of the explanation is, although I have these lines here indicated in colour, when you're drawing them onto the sheet here, put them in very, very light pencil. So once we have those lines going off to the vanishing points, we then look at the solution here that is provided, the 3-dimensional graphic that's provided on the solution. And you can see here that we have these lines going off there in that direction, again towards VP1. We have our small little vertical line there. There's the vertical line there. And then that line goes back over to VP2. Now, there are still a few elements of the drawing that we're missing. We are missing a point here, and we're also missing a point over here. Now again, looking at this drawing, we will get the information that we required. If you look at this corner up here that we're looking for, it is directly above that corner. So to get the point that we're looking for here, we extend up this corner until it hits this line, and then we can heavy from there to that point and back down to that corner. In relation to this corner here, you can see that we have to drop down that corner onto the ground and then bring it back to locate this corner. So this line must come down here onto that line and then go back over to VP1. And when that cuts this projection line here, that will give us the corner we are looking for. So to get this point here, I brought up that point there as a vertical line. That gives me that point there I'm looking for, and I can continue this line over to meet that and then back down to that corner. And that completes the lid of the piano. And then going back over here, looking at that corner, it was dropped down onto this line and then brought back to VP1. So therefore we drop this line down as a vertical line, bring that line is heading towards VP1. And as that cuts this line coming from here, that gives us the corner we're looking for, and we join that in. And that then completes that perspective drawing. It is important to look at the 3D graphic very, very carefully. There's a lot of information on that will help you solve the actual question itself. So that completes the perspective drawing question 2. Moving on to question 3. The question states, the figure shows the outline of a pair of 3D cinema glasses based on 2 regular pentagons. Write down the measurements of A, B, and C. So, dealing with A first of all. A points there to the top of the circle and to the bottom of the circle. So we're looking for the diameter of the circle. We are told there that the radius is 15 millimeters. So the diameter is going to be twice the radius, and therefore A is going to be 15 plus 15. A is 30 millimeters. So looking at the next part of the question, getting the dimension for B. Now B is this distance here between the end of this circle and the center of this one. But we are told that the distance from the end of this circle to the end of this circle is 74. Now if we look at the distances that we have to eliminate, 15 millimeters there of that circle has to be eliminated to bring us from here to here. And then if we look at this circle, which is diameter 30, we have to take that distance away from there. So the length of B is going to be 74 minus 30 and minus 15. So that's 74 minus 45. So just again to make sure that we have this correct, it is no harm to have a calculator with you inside the exam. So we have 74 minus 45, 29. The distance from the dimension there of B is 29 millimeters. The next thing that we have to do here is we have to find the measure of this angle C. Now, one way you can do that is to use your protractor, but in order to get an accurate measurement with the protractor, you have to extend on the sides of the pentagon. So I put my set square there and I have extended on this side and I have extended on this side here. So once we have extended on the sides of the pentagon, we then take our protractor and put it down on the angle to measure it. When you're measuring the angle, it's important that the center of the protractor is on the corner of the pentagon and that the 0 line is in line with one of the sides of the pentagon. So once we have that established, where we have the center of the protractor on the corner and 0 lined up with this line, we then move around to measure the angle. Now you can see there's 110 degrees, and then moving back we have 100. So this line is in the 100 to 110. And if we count back, it's 1, 2 back. So that angle there is 108 degrees. So the internal angle of a pentagon as measured by a protractor is 108 degrees. Now, it is perfectly acceptable to measure the angle using a protractor in the exam. The other way of working this out is that if you take the number of sides on a pentagon, and there are 5 sides on a pentagon, and if you divide 360 by 5, you get 72. And 72 degrees is the angle that we usually set up a pentagon. But as you can see here, this angle is clearly not 72 degrees. It is more than 90. So how can we calculate that mathematically? Well, if you take the setup angle of 72 degrees away from 180, you are left with 108 degrees. So that's another way of doing it, solving it mathematically. So 72 degrees, the setup angle that we use for a pentagon, minus that from 180, leaves us with 108 degrees. And that is also another way of calculating angle C. So to get angle C, you can work it out using a protractor as we did in the first part, or you can work it out mathematically. Both methods are correct. So the finish of that question, A is 30, B 29, and C is 108 degrees. Question 4. The elevation and end view of a weighing scales are shown on the square grid. Make a freehand pictorial sketch of the weighing scales. Color or shade the sketch. Now, it is very important when you're doing this that it is a freehand pictorial sketch. If there is any evidence of a ruler being used in this, the question is no longer marked out of 12, it's marked out of 6. So if there's any evidence of a ruler being used or a set square being used to solve this question, you will lose half the marks for it straight away. So we have to use the grid to produce an accurate sketch of the weighing scales. Now the solution to this is all about thinking what this is going to look like in 3 dimensions and counting the dots. Now if we go over here to the orthographic views, the elevation and the end view, you can see to get from that point there, we have to go out 1, 2 dots. And that brings us to the bottom. And then to get the top corner from here, we have to go up 1, 2, 3 and out 1. So we have to go out 2 to get the bottom, then up 3 and out 1 to get the top. So if we go over here to this drawing, you can see there from this line that was indicated for us, I've gone out 2 to get the bottom. But then I count up vertically 1, 2, 3 dots. And then I come back 1 to get this one here, and now I have the top corner. Now, if we look at this here, we can see that the total width of that is 1, 2, 3, 4. So from this point here on the bottom, count over 1, 2, 3, 4, and that will bring you to that position there. And then again, we go up 1, 2, 3, and back 1 to get that point. And then we'll connect those with a line there, and that completes that surface there. Now, once we have this surface completed here, that is the start of the top of the weighing scales. So now we need to get the length of it. And if we go over here and we count the dots that we're dealing with, right? So to get the length of this line here, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And on the bottom, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So we have to go 10 along the top and 8 along the bottom to get the top and the bottom portion of the weighing scales. So after establishing this corner here, we count over 10, and that will bring us to this corner here. And once we have this corner here, we go over 8, and then we connect those together. Now you can see here that this is 3 high, and we want to show the internal detail here of the weighing scales because this would be open. So from the line at the back here, again, you can drop down 3, and this line will be going over here. And again, we just bring that corner, and then that line would emerge. And this line here at the back would be running parallel to that. So we don't need to find a dot. If you can just, this is a sketch. So if you just take that line and sketch parallel to that. And as long as you get a reasonably parallel line, that will give you this line here at the back. And that's the internal detail of the scales. So from that corner over 10, from this corner over 8, connect those together. Then drop down 3, draw this line going back. This line here is parallel to this line, and then that corner would be coming along those dots, and then it would emerge out here to give you the internal corner there. Finally, to complete the scales, we're now looking for this line here. Now the thing to be careful with is the middle bit here is inset off the front of the weighing scales by a distance of 1. So if we take that corner and if we let that run up to there, where this line is coming into is 1, 2, 3 away from this edge here, but it is inset off the face 1. So if we take that this corner here is lined up with that corner, which it is, and then if we go back 1 there, and then count in 1, 2, and 3, that dot there is where this line will be heading to. So once we get this line here, the length of the front of it, which is too short of the end there like that. So from this line going back, we count back 2. That line would be heavy to cross the front there like so. Then this line is heading up into this dot here, which is that corner brought back 1, 2, 3, and that line is heading into that point. So once you have that done, and then once you have that line, then you can draw this line going back until it disappears behind that. That there is your weighing scales completed. So now we have to apply a small bit of colour to make it look a little bit more realistic. When you're applying colour and shading to the drawing, it's important to consider where the light is coming from. So I'm assuming that the light is coming here from the back, which means that this top surface will get lit up, this front surface a little bit more, but this back surface here will be completely in shade. So what we want to do is we want to subtly change the shading. So this is a very, very light green here on top, slightly darker green here on the front, and then a very, very dark green there at the back. Likewise, difficult to see the variation, but we have a light yellow here at the front and a slightly darker yellow here at the back. And then we have the grey area here at the front and a darker grey, and then light in here because this will be getting all the light from the top. So just try to subtly change the difference in the shading to think about the light and where the light is coming from. And that then completes the three-dimensional view, freehand sketch of the weighing scales. So moving on here to question 5. Shown is a graphical puzzle consisting of squares, rectangles and triangles. Count the number of squares, rectangles and triangles. Now, this is a little bit more difficult than it looks. You have to be very, very careful to make sure that you're spotting every one of the 3 geometric shapes. So how many squares do we have first of all? Well, first of all, we have the perimeter square, so that's 1. Then we have this small square here, which is 2. Then we have this other square here, and that's 3. And then you have this tilted square inside, which is 4. So we have the perimeter, 1, this square here 2, another square here, which is 3, and the tilted square, which is 4. So 4 squares all together. Okay, moving on to the rectangles. So the first rectangle that we have is a rectangle that goes from the top to the bottom over here, back up. So there's 1 rectangle. Then we have the same rectangle over here going from this direction over here. So there's 2. Then we have 3, and then we have 4, 5 and 6. But now we have this bigger rectangle going from the top across the bottom and up there. So there's another rectangle, And then likewise, we have this rectangle here running in that direction. So that gives us a total of 8 rectangles altogether. So again, we have this one that goes from the top to the bottom is 1, from here to here is 2, the smaller one 3, the smaller one here 4, 5 and 6, and then this big one here 7, another big one there 8. 8 rectangles in total. Now getting all of the triangles is quite complicated. So let's begin here, where in this area in here, and counting the triangles that we have. So the most obvious ones here is we have this one here, which is 1. Then we have this one here 2. We have 3. And then we have 4. Then we have 5, 6, 7 and 8. 9 and 10. We have this big triangle running in that direction there, so that's 11. And then we also have this one here, which is 12. And then we have another triangle running from there to there, up to there and back down, 13 and 14. So 14 triangles altogether. Despite it looking easy, that is a very, very complicated question. It requires an awful lot of visualization, and for you to really think about what you are looking at and interpreting all the different geometrical shapes. The fact that each shape is subdivided does make the visualization of it very, very difficult. But you just have to keep looking and keep looking until you are happy that you have accounted for each of the 3 different types of shape. Question 6. The figure below shows us the elevation of a stapler. A 3D graphic is also shown. Rotate A, B, C, D, E about O until the point E reaches the line L, L1. So, as the question states, rotate all the points about point O until the point E reaches the line L to L1. So I have put the point of my compass there, and all points E, D, C, B and A, I have rotated those points about point O. Now, the important thing to remember about the short questions is every time you do something that is part of the solution, you get marks. So for swinging each one of those arcs was a mark each. So you can see there 5 arcs equal 5 marks. Now we have swung E up until it hits the line L to L1. So that is E in its new position. Now if we look, E, O and A are all on a common line, and O does not move because that is the point of rotation. And we know that A has to be on this arc here because that is the arc, the path that A is going to follow. So to get the base of the stapler, we know E is in this position on L1. O is not moving, so I can draw a line from here through O onto the arc there where A, and that is the base of the stapler. So once we've swung E up here onto the line L1, we label that point E1 because that's E in its new position. Now we know that E is connected to O and O's not moving, so we can draw a line from E to O, and then extending it out further onto the arc there from A gives us A1. That there is the base of the stapler after it has been rotated into that position. Now, the other thing that we know is the distances between points are not going to change. So the next thing that I want to do is I want to get D. So if I take my compass there and I measure the distance using my compass from D to E, that distance remains constant. And if I take my compass now and put the point on E and then swing an arc onto this swing an arc from E with the compass onto this arc coming from D. That will give me D in its new position because that distance must remain constant. So take the distance from E to D on your compass, place the compass on E1 and swing an arc onto the arc coming from D. So after swinging the distance there from E up to D, it gives you this point here, and then we can connect a line from E1 to D1. Now if we look down here, we can see that this line CD is parallel to the line going from A to O to E. So this line and CD are parallel. So taking your set square and using sliding set squares, line up your set square there with OE, and then slide that out there accurately and draw a line from D down to the arc that C is on, and that locates C1 in this location here. So now we have to find point B, and again the distance there from C to B is a constant distance. So in order to get B1, use your compass again to take the distance from B to C, and then placing the point of your compass there on C1, swing an arc onto this line here to get B1, and then that completes all the points have been found. So we join from C1 to B1 and then back to A. So there we have the stapler in its rotated position. So again, follow what the question's asking you to do. It tells you to rotate all the points about O. So do that first of all. We rotate A about O, B about O, C, D, and then this is the important one, E, up onto the line L to L1. And that then gives us the starting point for the new drawing. Now we can see there that E, O and A are all on the one line. So in the new drawing, E1 to O to A1 must also be on the same line. So we draw that. The distance from E to D is a constant distance. So if you take that distance onto your compass, put the point of your compass on E and swing an arc from E to get D1. And then we know that this line C1 to D1 is parallel to this line. So we draw a line parallel to that. Then we know that the distance from C to B is constant. So take that on the compass, put it on C, swing an arc. That then locates all the points. And that then is the stapler in its rotated position. And that completes question 6. Question 7. The figure shows the outline, elevation and plan of a security camera. A 3D graphic is also shown. Project an auxiliary elevation of the camera on the line X1, Y1 to show the true shape of surface S. So this is what we call auxiliary projection. Here we have the elevation and the plan of the camera. But because as we look in here at the elevation, this surface here is at an angle to our field of vision, you do not see the true shape of surface S. In order to get the true shape, we have to orientate our view that we are looking at this surface at an angle of 90 degrees. So the first thing of this drawing is that we have to project off at 90 degrees to this surface. So it's a continuation of those lines. Bring up those lines there at 90 degrees to surface S and project them up here to where the X1, Y1 line is. So the first thing that we have to do to solve this question is that these sides and the circle and the dotted line and the end of the camera have to be projected up into this view. Now it's just a continuation, but these lines must cross the X1, Y1 at an angle of 90 degrees. So you project up from the plan these lines, and again they must cut the X1, Y1 at an angle of 90 degrees. Now this view here is being projected from plan. So therefore this is an elevation. It's an auxiliary elevation. and heights do not change from one elevation to another. So whatever the height of the points are in this elevation, they must be the same height in this elevation here. So over here I have drawn a height line, and I have marked up H1 and H2 and the ground then H0. So there are three heights that we have to consider. H0, which is the ground, H1, which is where all these points are, and then H2, which is the ultimate height of the camera. So once you have that line drawn there, again, parallel to the projection lines, you draw your height line out over here, and you take the same height here. The distance from the XY line up to H1 is the distance that we mark to H1 here, and the distance from H1 to H2 is the distance that we mark up here. So now we have our situation where we have all the points projected from the plan, we have our heights established, and now we're ready to complete the final part of the drawing. So looking here at surface S, we can see that this side here is sloping, this side here is a vertical line, and we also have then the portion of the camera, the support of the camera here. So dealing with the actual body of the camera, this line here is going to be the top. We know that because this line, because it's put it in as a dashed line, is the hidden detail line that's on the bottom. So when you project up this here, you get that point there, and then we have the hidden detail line down here, so we connect them together with a diagonal line. Then this line runs along the bottom here to the very end of the camera. So the dotted line there, you'd have the line running on to the very end of the camera. So this line runs to here, and then it goes all the way up to H2 and then back to the original position. And there is the true shape of surface S. Now the only other thing then that we have to consider is the little support here. So from the circle there, we take the extreme sides of the circle. As that goes up, then it gives us a heavy line there and a heavy line there. And that completes question 7. That completes question 7, which shows an auxiliary elevation, which shows the true shape of surface S. Question 8. The elevation and plan of a measuring tape are shown. In the space provided, draw a freehand pictorial sketch of the measuring tape. Color or shade the completed sketch. Now, again, it's important to again emphasize that if any drawing equipment is used in the solution of this, the question will be marked from 6 marks instead of 12. So if you're dealing with any question where it specifically outlines that you have to produce a freehand pictorial sketch, you must do it freehand. Any evidence of using drawing equipment, the question will lose half the marks straight away. To produce the sketch of this measuring tape, we first of all begin by drawing a box. Now again, to show it in 3 dimensions, you have to draw a line running off here at an angle in that direction and a line running off here at an angle in this direction. Then it's all about keeping the lines parallel. So we extend up a vertical line here, a vertical line and a vertical line. And these lines going off in that direction must be parallel with all of those, and these lines running in that direction must be parallel. So we begin by just drawing a box, because out of that box there, we will be able to form the shape of the measuring tape. So once we have our box drawn, we then want to cut off this corner here. So we start down quite low and we draw this wide sweeping arc to come in here and meet there at the top. So we draw an arc there from the front face to this position here. And then on the front face here, we draw a similar arc, again, trying to make both arcs end up parallel to each other. Then we want to draw the position of the measuring tape. So we just draw a line there coming out there like that. Then we bring a line out parallel to these, trying to keep so that it doesn't make the tape look like it's bent inwards. So with those lines there, extend the tape out in that direction, drop it down, and you just want to show that it has a little bit of thickness. So just bring that back there a very, very small amount, and then let that run in here, and then that gives us the tape going into the measuring tape. We also have this pattern here on the front. So again, it's just a line going back to this corner up, and then curved it around to try and follow the curves here that we've already drawn on the measuring tape. So now we draw the position of the locking button up on top of the measuring tape. So we draw a line off in that direction and a line off in that direction, and then we draw 3 very, very small lines there to bring us from the bottom surface up to the top, and then we draw the top surface there on that. Now that there is a rough drawing of the measuring tape, just drawn lightly just to get the basic shape of it correct. And then once you have that done, we'll further refine that with the pencil now to make it stand out a little bit more. So by going over the lines, we further smoothen out the sketch that we've drawn, and it makes it look a little bit more definite on the page. Couple of little things there, just these buttons tend to have grips on them, so I've just drawn a few vertical lines to give it the texture of a hand grip. And then also then that we have this steel area here, which in order for the tape measure to catch on a piece of material, this piece of steel, and that then would normally come in here and it would be screwed in position. So just little features there like that can make all the difference to the drawing. So then we want to apply some color and shading to that. So once you have your sketch done, you apply then the color and the shade to it to make it look as realistic as you possibly can. And that then completes question 8, which is the sketching question. So the CAD commands. So we have this arrangement here, and it's taken through a number of different stages, and we have to write in the CAD commands. Now, there will always be 4 CAD commands, but you only ever have to give 3. So if you look here, we have a line, and the line is slightly short of this point. And if we look at this next one, the line has been extended to meet it. So there's the first command that we have to write in, and that is extend. Now, looking at this, we've now gone from this situation where you can see you have this figure here, and then it is flipped over onto the other side. So what has happened there, it has been mirrored. The image has been mirrored, that we have used this axis here, and then these lines here have been mirrored across this to produce this figure here. So that then is the second command, mirror. So after we have mirrored the image across that line, moving on to this next one, you can see that we have a similar shape to the outside, but it is in a small bit from the outside shape. It is offset from the outside shape, and that is the command that we use there for that. To bring this shape in is the command offset. And finally, we have our 2-dimensional shape there, and now we've gone into a 3-dimensional shape. So the commands then to turn the 2-dimensional shape into a 3-dimensional shape is extrude boss base. So the different commands. So first of all, we have a line that's short and we need to make it longer. The command is extend. Then we have this image here and we want to flip it over, so the command is mirror. Then we have this larger figure and we want to bring in a smaller one, the command is offset. And then to turn 2-dimensional into 3D, it's extruded boss base. Now, when you're doing this question in the exam, you should always try to write down the 4 commands, because if you get one wrong, you will still get full marks awarded to you. So if you can, always write down the 4 different command options. And that completes question 9, the CAD question. Question 10. Figure 1 shows a design for a glamping pod. Shown in Figure 2 is the incomplete elevation of the glamping pod. Complete the elevation in Figure 2 by constructing a parabola in the rectangle ABCD with its vertex at O. Show clearly all construction. So the first thing we do here is we draw a line at any angle from B, and using our compass we step out 5 equal divisions down along that line. The last division we join back to A, and then using our sliding set squares we line up a set square there with this line, and then we go back, bring that point there and that point, and that will divide that line up into 5 equal parts. In a similar way we draw a line at any angle away from O. Again, using our compass, mark 5 equal divisions along that line. The last one join back here to this, and then using sliding set squares, bring these lines back parallel, dividing this top line into 5 equal parts. So when you have that divided up into 5 equal parts, on this side here, these lines must go to the vertex at O. So all of these lines here, we draw diagonal lines from this position up to point O, and then that completes this side of the drawing. So once we have those diagonal lines drawn, then we go to the top here and we drop down vertical lines. So bringing this point down vertically, that gives us our first point here. Bringing this line down onto the next line here gives us our second point, our third, our fourth, and our fifth. So you mark those points very carefully, and then the next stage of the drawing is to connect those with a curve down to A. So we connect those points together with a curve, and that gives us half the parabola. Now, you could set up all of this construction again on this side, but that is going to be very, very time consuming. A much better method is to use this center line and just mirror the points across. So if I bring that point, this point here across, and that point there and that point, and then measure the distance from the center line to the point, and then flip that to the other side, I will produce the parabola on the other side without having to draw all of this construction, and it is a lot quicker to do it that way. So the first thing we do is everywhere we have a point on the parabola on this side, we just bring a horizontal line straight across to get the points here in this position. And then taking the distance on your compass there from the center line to the first point and flipping that over there to the other side, you mark your points into this location. Then you go up, you have to shorten the distance for the next point. So we take the distance from the center line to that point, flip it over, center line to this point and flip it over, and then finally from this point to this point. And what we've done there now is we have produced exactly the same points in the exact same location as we have on this side. Connect them together with a curve. So we draw the curve on the other side, and that completes the parabola, and that completes question 10. Constructing a parabola to form the glamping pod. Question 11 on developments. Figure 1 shows the development of an object. 3 images of objects before development are shown on the right. From the images on the right, match the letter for the development shown in Figure 1. So if we look at this arrangement here, we have to imagine what this is going to look like folded up, and then we have to see which one of these will it form. So if you look at this here, if you fold up that side, and if you fold up that side, and if we fold up the back, that means that this corner is going to meet with this corner, and that's going to create a right angle at the back, and that's fine. Now if we look here, we have this front surface which is going to fold up along there. We're going to have this surface here which goes along there, and then we have this little upturn here. So it's going to form a completely, so the object when it's folded together is going to be enclosed except for this portion at the top. So when we go over here and look at these, we can see that A has this open area here at the back. And if you look at that there, this will fold up, so it can't be A. If we look at C, you can see there that C is enclosed at the top, and we've already just identified that it cannot be C because this top portion here, if we look at how these are going to fold up, that the top portion is going to be open. So if you look at B, you have the back there is sealed up, and we have the surfaces there going up along that surface, leaving an open top. So B is the correct answer. Question 12. The incomplete outline of a shelf support is shown. A 3D graphic of the support is also shown. Complete the outline of the support by constructing the internal tangent between the two given circles. So for the solution to this question, anytime you're dealing with a tangent to a circle, you have to think of drawing a semicircle. So the first thing that we have to do is we have to connect the center of the big circle to the center of the small circle. Using our compass, then we have to bisect the distance. So taking a distance of greater than half the line, and from the center of the small circle I swing an arc above and below the line, and from the center of the big circle I swing an arc, and I draw in the bisector, and then that will give me the center point of this line. You don't have to draw the semicircle here, but we do have to draw the semicircle on this side in this location up here. So with the point of your compass there, open up the with the point of the compass there, open the compass to the center of this and swing it around, and it should finish on the center of the small circle. That's the first stage of this question. So now I take the radius of the small circle. I take the radius of the small circle, and with that distance I place that onto the circumference of the big circle, and I add the radius of the small circle to the big circle. So we take the radius of the small circle and we add it to the radius of the big circle. Then, opening up your compass, put the point of the compass on the center of the big circle, and taking the radius of the big circle plus the small circle, swing up an arc until it intersects the big circle at this point here. So once we've added the radius there of the small circle to the big circle, we swing that up there, and that gives us this point where this arc cuts the semicircle. So where that arc cut the semicircle gives us this point here, Q. From the center of the circle, we draw a line up to Q, and that there is the first normal. And where that normal cuts the circle here gives us our first point of contact where the tangent will be running from. Now, after that, we need to get a normal on the smaller circle down here. So the normals have to be parallel. So using your sliding set squares, line up your set square with the normal up here, and then sliding it down until you pick up the center of the small circle. Draw the second normal coming out from the center of the small circle out in this direction. And then that gives you the second point of contact here. So our internal tangent will run from this point up to this point. Where the normals intersect the circumference of the circle will give us the tangent we're looking for. Now, there is quite a bit in this, and tangents to circles, the construction can seem a bit complicated, but it is all based on a semicircle. So the first thing that we did was we have to draw from the center of the big circle to the center of the small circle. Then once we've done that, we bisect that distance and draw on the bisector, and we draw in this semicircle here. Now, after that bit there is very simple and straightforward. There's no complicated issue with that. After that, now it does become a little bit where you do need to be thinking about what you're doing. So the next stage is, if you want to get an internal tangent, which is what's specified in the question, an internal tangent, which is a tangent that goes inside the circles, we take the radius of the small circle and we add it to the radius of the large circle. Then, putting the point of our compass here, we swing that up to get Q, and then we join from the center up to Q. That there is the normal, and the tangent is at 90 degrees to the normal. Now, as that line cuts the circle there, that gives you the point of contact at P, and then, as we said, using our sliding set squares, we transfer that down into this location, and we draw the other line coming out in this direction, and that gives us the other point of contact down here, P, and you draw your tangent between them. Now, that's an internal tangent. If you were asked for an external tangent, which is a tangent that stays on the outside of the circles, the difference there is you take the radius of the small circle, but instead of adding it to the radius of the big circle, if you want a tangent on the outside, you have to mark that distance, the inside of the circle. Now, I know that sounds probably a little bit confusing, all right? So what we'll do is we'll have a look at those questions independent on their own. You have to know the construction of tangents to circles. They are very, very important. But in relation to this question here, that there is the solution. Connect the centers, bisect, semicircle, radius of the small circle added to the radius of the big circle, swing an arc, draw the normal from here up to Q, locate P, transfer that line down here, locate the other point of contact, then the tangent goes in between the 2 points of contact. That there completes question 12, an internal tangent between two unequal circles. Question 13. The figure shows the outline of a house. Draw a new outline similar to the given house, where the length AB increases to AB1. So the solution to this question is what we call polar projection. Now, it's kind of like a single point perspective, whereas if you want to reduce something in size, the closer you bring it to A, the more reduced the shape is going to be. Or if you want to enlarge it, the more we go away from A, the bigger it's going to get. So the first thing is we have to use A as our point, and then from A, we radiate lines out through all the points of intersection. So every corner that we have on the object, I bring a line from A through all of those points. So lining up your set square with A, we extend out that side. This corner here, extend out a line. That corner, extend out a line. This corner, this one, and finally that one. Extend the line out through all of those points. So once you have brought the lines out from A, then we look at our original drawing, and we can see we have a line from B that goes up to this line here. So going out to B, we extend a line onto this line coming through the top corner of the chimney. We extend that up to here. Then this goes along flat until it hits this projection line. So again, this must continue on flat until it hits the line containing that corner. Then it drops vertically down until it hits this corner here. So extending that line out there, this comes down until it hits that line. Then it goes parallel to this line. So using your sliding set squares, line up your set square with that line, and then bring that over there like that, and then transfer this corner onto this line where the two roofs are meeting. We bring that line up, and then finally parallel to this line here, this line comes down to meet this, and then that is the enlargement of that shape, and that completes question 13, the enlargement. Question 14. The graphic shows a set of steps. Draw a well-proportioned freehand sketch of the plan of the steps. So a plan is going to be a view looking down, which means we're going to see this surface with a little curve on it. One rectangle, two rectangle, and this one with a curve on it. So moving over here, you draw this shape coming down and the curve going back in here like that, and then you complete that rectangle there. We draw 1, 2 rectangles coming out there like so, and then you start a third, but the corner of it is taken off, and that's what the plan would look like. Now again, it's important to remember it does say it's freehand, so if there's any evidence of using drawing equipment, again, you lose half the marks for it. So that there is the plan of the steps. When you're drawing that, again, it does say make it well proportioned, so try to keep those measurements there even, judging them by eye. Finally, question 15. Car sales in a garage were recorded over a period of 6 months. The following are the results: January 50, February 30, March 55, April 15, May 25 and June 45. Complete the chart to represent this information graphically. Now, this question is very straightforward and there's not a lot to be said about it, but one thing that I would encourage you to do is always number the vertical axis, because without numbers here it is very, very easy just to take a line above or below the point you're looking for. So by numbering these off here, it makes the question very, very easy. So the first two we were given at 50 and 30, and those are indicated there. So March was 55, so there's 55 and we get our point there. And I'm not going to say any more about it. You plot the other points there and that completes the graph. That there is the completion of question 15, and that completes the short questions for the 2019 Technical Graphics Higher Level Paper Section A short questions.